In this video, we're going to discuss the Atwood machine and how it works with rotational motion. So let's look at this problem together. It says we have an Atwood machine with radius r and a moment of inertia of I. So an Atwood machine, if we remember correctly, is a pulley with two hanging masses, M1 and M2. And I'll have M2 being larger, so it rotates around. Well, this pulley now has some rotational inertia. All right, so actually the problem says that we have M2 or M1 moving down and M2 moving up with a speed of v. And they're attached by a string that's not going to stretch, so we assume that their speeds are the same. We want to know what's the magnitude of the total angular momentum of the system. What is L? Well, the first thing I'm going to do is I'm going to actually look at the direction that these things are going to point. And I see that this mass right here, this mass 2, is moving in the upward direction. And if I were to look and see the radius that it's attached at, or the radius is actually over here, but I know I'm going to need the perpendicular component, because I remember that one of my equations for angular momentum is r cross p. Well, I know that that's the perpendicular component of these. So I know I have p going up, and I have my r going out. So when I look at this, I'm going up, or I have, let's see, radius over, p going up. So I have radius over, p goes up. That means my thumb points into the page. So this angular momentum of 2, is in the negative z direction, z hat direction. I'm going to say that I have x, y, and z is out of the page. So negative z in that direction. Same thing with mass 1. I'm going over, my radius is over. I curl my fingers in the direction of p because p points down. It's in the direction of my velocity, which means L1 is in the negative z hat direction as well. It points into the page. And if this whole thing spins, this whole thing is spinning, that means my angular velocity is into the page as well, the negative z hat direction, which means the moment of inertia times the angular velocity gives me my angular momentum of this guy. This is also into the page. So the good thing is that all three of these values we add up together. So that actually allows me to probably eliminate a few things out. I can eliminate out the minus ones because I know that m is positive, v is a positive magnitude, r is a positive magnitude. The only way we get this minus sign is if they're moving in different directions. But the momentum, the angular momentum, because this one's moving up and this one's moving down, both of these two angular momentums are both directed into the page. So what do we need? Well, we need to just add these values up. Well, I know that I have r cross p, and I know that they're perpendicular to each other. So this is rp, or rmv, r1, m1, v1, plus r2, m2, v2. It's going to give me my total angular momentum, plus the moment of inertia times omega. And that will deal with the moment of inertia of the wheel. So this is mass 1, this is mass 2, and this is the pulley itself. So I get m1 plus m2 vr, that's nice, it's in both cases, plus I v over r squared. Well, the last equation that I bring in is that v is equal to r omega, or v over r is equal to omega. So when I substitute this in here, I find that answer choice B is my correct answer. I have the moment of inertia, or the angular momentum of mass 1, angular momentum of mass 2, because they're both They both have momentum at a distance away. They have a cross product. And I have the moment of inertia times the angular velocity to give me my angular momentum of the pulley itself. All three of them add together, so I should have plus signs all the way through. And I can actually do one better on here. They give me the moment, they give me that its a magnitude is this value, but I also know that it's directed into the page. That's the direction of that vector.